A manual transmission, also known as a manual gearbox, stick shift, standard transmission, 46-speed or simply a manual, is type of transmission used in motor vehicle applications. It uses a driver-operated clutch engaged and disengaged by a foot pedal or hand lever, for regulating torque transferred from the engine to the transmission, and a gear selector operated by hand or by foot. A conventional, 5 or 6-speed manual transmission is often the standard equipment in a base model car. Other options include automated transmissions such as an automatic transmission, a semi-automatic transmission, or a continuously variable transmission. Overview: manual transmissions often feature a driver-operated clutch and a movable gear stick. Most automobile manual transmissions allow the driver to select any forward gear ratio at any time, but some, such as those commonly mounted on motorcycles and some types of racing cars, only allow the driver to select the next higher or next lower gear. This type of transmission is sometimes called a sequential manual transmission. The way a manual transmission works is that the flywheel is attached to the engine, the clutch disc is in between the pressure plate and the flywheel. When running, the clutch disc spins with the flywheel. As the clutch pedal is depressed, the throw-out bearing is pushed in, which makes the pressure plate stop applying pressure to the clutch disc. This makes it stop receiving power from the engine so that the gear can be shifted without damaging the transmission. When the clutch pedal is released, the clutch disc is allowed to start receiving power from the engine. Manual transmissions are characterized by gear ratios that are selectable by locking selected gear pairs to the output shaft inside the transmission. Conversely, most automatic transmissions feature epicyclic gearing controlled by brake bands and/or clutch packs to select gear ratio. Automatic transmissions that allow the driver to manually select the current gear are called manumatics. A manual-style transmission operated by computer is often called an automated transmission rather than an automatic. Contemporary automobile manual transmissions typically use 4 to 6 forward gears and 1 reverse gear, although automobile manual transmissions have been built with as few as 2 and as many as 8 gears. Transmission for heavy trucks and other heavy equipment usually have at least 9 gears, so the transmission can offer both a wide range of gears and close gear ratios to keep the engine running in the power band. Some heavy vehicle transmissions have dozens of gears, but many are duplicates, introduced as an accident of combining gear sets, or introduced to simplify shifting. Some manuals are referred to by the number of forward gears they offer as a way of distinguishing between automatic or other available manual transmissions. Similarly, a 5-speed automatic transmission is referred to as a 5-speed automatic. Unsynchronized transmission. The earliest form of a manual transmission is thought to have been invented by Louis Reiner, copyright Panard and Emile Levasseur in the late 19th century. This type of transmission offered multiple gear ratios and, in most cases, reverse. The gears were typically engaged by sliding them on their shafts, which required careful timing and throttle manipulation when shifting, so the gears would be spinning at roughly the same speed when engaged. Otherwise, the teeth would refuse to mesh. These transmissions are called sliding mesh transmissions or sometimes crash boxes, because of the difficulty in changing gears and the loud grinding sound that often accompanied. Newer manual transmissions on cars have all gears mesh at all times and are referred to as constant mesh transmissions, with Synchromesh being a further refinement of the constant mesh principle. In both types, a particular gear combination can only be engaged when the two parts to engage are at the same speed. To shift to a higher gear, the transmission is put in neutral and the engine allowed to slow down until the transmission parts for the next gear are at a proper speed to engage. The vehicle also slows while in neutral, and that slows other transmission parts, so the time in neutral depends on the grade, wind, and other such factors. To shift to a lower gear, the transmission is put in neutral and the throttle is used to speed up the engine and thus the relevant transmission parts, to match speeds for engaging the next lower gear. For both upshifts and downshifts, the clutch is released while in neutral. Some drivers use the clutch only for starting from a stop, and shifts are done without the clutch. Other drivers will depress the clutch, shift to neutral, then engage the clutch momentarily to force transmission parts to match the engine speed, then depress the clutch again to shift to the next gear, a process called double clutching. Double clutching is easier to get smooth, as speeds that are close but not quite matched need to speed up or slow down only transmission parts, whereas with the clutch engaged to the engine, mismatched speeds are fighting the rotational inertia and power of the engine. Even though automobile and light truck transmissions are now almost universally synchronized, transmissions for heavy trucks and machinery, motorcycles, and for dedicated racing are usually not. Non-synchronized transmission designs are used for several reasons. The friction material, such as brass, in synchronizers is more prone to wear and breakage than gears, which are forged steel, and the simplicity of the mechanism improves reliability and reduces cost. In addition, the process of shifting a Synchromesh transmission is slower than that of shifting a non-Synchromesh transmission. For racing of production-based transmissions, sometimes half the teeth on the dog clutches are removed to speed the shifting process, at the expense of greater wear. Heavy-duty trucks often use unsynchronized transmissions, though military trucks usually have synchronized transmissions, allowing untrained personnel to operate them in emergencies. In the United States, traffic safety rules refer to non-synchronous transmissions in classes of larger commercial motor vehicles. In Europe, heavy-duty trucks use synchronized gearboxes as standard. Similarly, most modern motorcycles use unsynchronized transmissions. Their low gear inertias and higher strengths mean that forcing the gears to alter speed is not damaging, and the pedal-operated selector on modern motorcycles, with no neutral position between gears, is not conducive to having the long shift time of a synchronized gearbox. On bikes with a 1N2-3-4 transmission, it is necessary either to stop, slow down, or synchronize gear speeds by blipping the throttle when shifting from second into first. Synchronized transmission. Most modern manual transmission vehicles are fitted with a synchronized gearbox. Transmission gears are always in mesh and rotating, but gears on one shaft can freely rotate or be locked to the shaft. The locking mechanism for a gear consists of a collar on the shaft which is able to slide sideways so that teeth on its inner surface bridge two circular rings with teeth on their outer circumference, one attached to the gear, one to the shaft. When the rings are bridged by the collar, that particular gear is rotationally locked to the shaft and determines the output speed of the transmission. The gearshift lever manipulates the collars using a set of linkages, so arranged so that one collar may be permitted to lock only one gear at any one time. When shifting gears, the locking collar from one gear is disengaged before that of another is engaged. One collar often serves for two gears. Sliding in one direction selects one transmission speed, in the other direction selects another. In a Synchromesh gearbox, to correctly match the speed of the gear to that of the shaft as the gear is engaged, the collar initially applies a force to a cone-shaped brass clutch attached to the gear, which brings the speeds to match prior to the collar locking into place. The collar is prevented from bridging the locking rings when the speeds are mismatched by synchro rings. The synchro ring rotates slightly due to the frictional torque from the cone clutch. In this position, the dog clutch is prevented from engaging. The brass clutch ring gradually causes parts to spin at the same speed. When they do spin the same speed, there is no more torque from the cone clutch and the dog clutch is allowed to fall into engagement. In a modern gearbox, the action of all of these components is so smooth and fast it is hardly noticed. The modern cone system was developed by Porsche and introduced in the 1952 Porsche 356. Cone synchronizers were called Porsche type for many years after this. In the early 1950s, only the second-third shift was Synchromesh in most cars, requiring only a single synchro and a simple linkage. Driver's manuals in cars suggested that if the driver needed to shift from second to first, it was best to come to a complete stop then shift into first and start up again. With continuing sophistication of mechanical development, fully Synchromesh transmissions with 3 speeds, then 4, and then 5, became universal by the 1980s. Many modern manual transmission cars, especially sports cars, now offer 6 speeds. The 2012 Porsche 911 offers a 7-speed manual transmission, with the 7th gear intended for cruising top speed being attained on 6. Reverse gear is usually not synchromesh, as there is only one reverse gear in the normal automotive transmission, and changing gears into reverse while moving is not required, and often highly undesirable, particularly at high forward speed. Additionally, the usual method of providing reverse, with an idler gear sliding into place to bridge what would otherwise be two mismatched forward gears, is necessarily similar to the operation of a crash box. Among the cars that have Synchromesh in reverse are the 1995 to 2000 Ford Contour and Mercury Mystique, 0005 Chevrolet Cavalier, Mercedes 192.3-16, the V6-equipped Alfa Romeo GTV Spider, certain Chrysler, Jeep, and GM products which use the new venture Nevada, 3500 and Nevada, 3550 units, the European Ford Sierra and Granada Scorpio equipped with the MT75 gearbox, the Volvo 850, and almost all Lamborghinis, Hondas and BMWs. Internals, shafts. Like other transmissions, a manual transmission has several shafts with various gears and other components attached to them. Typically, a rear-wheel drive transmission has 3 shafts, an input shaft, a counter shaft and an output shaft. The counter shaft is sometimes called a less shaft. In a rear-wheel drive transmission, the input and output shaft lie along the same line, and may in fact be combined into a single shaft within the transmission. This single shaft is called a main shaft. The input and output ends of this combined shaft rotate independently, at different speeds, which is possible because one piece slides into a hollow bore in the other piece, where it is supported by a bearing. Sometimes the term main shaft refers to just the input shaft or just the output shaft, rather than the entire assembly. In many transmissions the input and output components of the main shaft can be locked together to create a 1-to-1 gear ratio, causing the power flow to bypass the counter shaft. The main shaft then behaves like a single, solid shaft, a situation referred to as direct drive. Even in transmissions that do not feature direct drive, it's an advantage for the input and output to lie along the same line, because this reduces the amount of torsion that the transmission case has to bear. Under one possible design, the transmission's input shaft has just one pinion gear, which drives the counter shaft. Along the counter shaft are mounted gears of various sizes, which rotate when the input shaft rotates. These gears correspond to the forward speeds and reverse. Each of the forward gears on the counter shaft is permanently meshed with the corresponding gear on the output shaft. However, these driven gears are not rigidly attached to the output shaft, although the shaft runs through them, they spin independently of it, which is made possible by bearings in their hubs. Reverse is typically implemented differently. See the section on reverse. Most front-wheel drive transmissions for transverse engine mounting are designed differently. For one thing, they have an integral final drive and differential. For another, they usually have only 2 shafts. Input and counter shaft, sometimes called input and output. The input shaft runs the whole length of the gearbox, and there is no separate input pinion. At the end of the second shaft is a pinion gear that mates with the ring gear on the differential. Front-wheel and rear-wheel drive transmissions operate similarly. When the transmission is put in neutral and the clutch is disengaged, the input shaft, clutch disc and counter shaft can continue to rotate under their own inertia. In this state, the engine, the input shaft and clutch, and the output shaft all rotate independently. Dog clutch. Among many different types of clutches, a dog clutch provides non-slip coupling of 2 rotating members. It is not at all suited to intentional slipping, in contrast with the foot-operated friction clutch of a manual transmission car. The gear selector does not engage or disengage the actual gear teeth, which are permanently meshed. Rather, the action of the gear selector is to lock one of the freely spinning gears to the shaft that runs through its hub. The shaft then spins together with that gear. The output shaft's speed relative to the counter shaft is determined by the ratio of the 2 gears, the one permanently attached to the counter shaft, and that gear's mate which is now locked to the output shaft. Locking the output shaft with the gear is achieved by means of a dog clutch selector. The dog clutch is a sliding selector mechanism which is splined to the output shaft, meaning that its hub has a teeth that fit into slots on the shaft, forcing that shaft to rotate with it. However, the splines allow the selector to move back and forth on the shaft, which happens when it is pushed by a selector fork that is linked to the gear lever. The fork does not rotate, so it is attached to a collar bearing on the selector. The selector is typically symmetric, it slides between two gears and has a Synchromesh and teeth on each side in order to lock either gear to the shaft. Synchromesh. If the so-called dog teeth make contact with the gear, but the two parts are spinning at different speeds, the teeth will fail to engage and a loud grinding sound will be heard as they clatter together. For this reason, a modern dog clutch in an automobile has a synchronizer mechanism or Synchromesh, which consists of a cone clutch and blocking ring. Before the teeth can engage, the cone clutch engages first, which brings the selector and gear to the same speed using friction. Until synchronization occurs, the teeth are prevented from making contact, because further motion of the selector is prevented by a blocker ring. When synchronization occurs, friction on the blocker ring is relieved and it twists slightly, bringing into alignment certain grooves or notches that allow further passage of the selector, which brings the teeth together. The exact design of the synchronizer varies among manufacturers. The synchronizer has to overcome the momentum of the entire input shaft and clutch disc when it is changing shaft to PM to match the new gear ratio. It can be abused by exposure to the momentum and power of the engine, which is what happens when attempts are made to select a gear without fully disengaging the clutch. This causes extra wear on the rings and sleeves, reducing their service life. When an experimenting driver tries to match the revs on a synchronized transmission and force it into gear without using the clutch, the synchronizer will make up for any discrepancy in RPM. The success in engaging the gear without clutching can deceive the driver into thinking that the RPM of the left shaft and transmission were actually exactly matched. Nevertheless, approximate rev matching with clutching can decrease the difference in rotational speed between the left shaft and transmission gear shaft, therefore decreasing synchro wear. Synchronizing rings are made of metal and can be provided with anti-wear coatings called a friction lining. Common metals for synchronizer rings are brass and steel. The linings typically consist of molybdenum, iron, bronze or carbon. The synchronizing rings are produced either by massive forming or sheet metal shaping. The latter involves the stamping of the blank out of a sheet metal strip and the subsequent machining with follow-on composite tools or transfer tools. A friction lining usually consists of thermally splashed molybdenum. Alternatively, iron or bronze sinter friction layers can be used. Carbon-coated synchronizer rings are particularly wear-resistant and offer very good friction behavior. Due to their higher price, these are reserved for high-performance transmissions. Reverse. The previous discussion normally applies only to the forward gears. The implementation of the reverse gear is usually different, implemented in the following way to reduce the cost of the transmission. Reverse is also a pair of gears, one gear on the counter shaft and one on the output shaft. However, whereas all the forward gears are always meshed together, there is a gap between the reverse gears. Moreover, they are both attached to their shafts, neither one rotates freely about the shaft. When reverse is selected, a small gear, called an idler gear or reverse idler, is slid between them. The idler has teeth which mesh with both gears, and thus it couples these gears together and reverses the direction of rotation without changing the gear ratio. In other words, when reverse gear is selected, it is in fact actual gear teeth that are being meshed, with no aid from a synchronization mechanism. For this reason, the output shaft must not be rotating when reverse is selected, the car must be stopped. In order that reverse can be selected without grinding even if the input shaft is spinning inertially, there may be a mechanism to stop the input shaft from spinning. The driver brings the vehicle to a stop, and selects reverse. As that selection is made, some mechanism in the transmission stops the input shaft. Both gears are stopped and the idler can be inserted between them. There is a clear description of such a mechanism in the Honda Civic 1996-1998 service manual, which refers to it as a noise reduction system. Whenever the clutch pedal is depressed to shift into reverse, the main shaft continues to rotate because of its inertia. The resulting speed difference between main shaft and reverse idler gear produces gear noise, grinding. The reverse gear noise reduction system employs a cam plate which was added to the reverse shift holder. When shifting into reverse, the fifth/reverse shift piece, connected to the shift lever, rotates the cam plate. This causes the fifth synchro set to stop the rotating main shaft. A reverse gear implemented this way makes a loud whining sound, which is not normally heard in the forward gears. The teeth on the forward gears of most consumer automobiles are helically cut. When helical gears rotate, there is constant contact between gears, which results in quiet operation. In spite of all forward gears being always meshed, they do not make a sound that can be easily heard above the engine noise. By contrast, most reverse gears are spur gears, meaning that they have straight teeth, in order to allow for the sliding engagement of the idler, which is difficult with helical gears. The teeth of spur gears clatter together when the gears spin, generating a characteristic whine. Attempting to select reverse while the vehicle is moving forward causes severe gear wear. However, most manual transmissions have a gate that locks out reverse directly from fifth gear to help prevent this. In order to engage reverse from fifth, the shift lever has to be moved to the center position between third and fourth, then back over and into reverse. Another widespread solution places reverse to the left of first gear, instead of behind the fifth. Similarly, many newer 6-speed manual transmissions have a collar under the shift knob which must be lifted to engage reverse to also help prevent this. It is clear that the spur gear design of reverse gear represents some compromises which are acceptable due to the relatively small amount of driving that takes place in reverse. The gearbox of the classic Saab 900 is a notable example of a gearbox with a helical reverse gear engaged in the same unsynchronized manner as the spur gears described above. Its strange design allows reverse to share cogs with first gear, and is exceptionally quiet, but results in difficult engagement and unreliable operation. However, many modern transmissions now include a reverse gear synchronizer and helical gearing. Design variations, ratio count. Until the mid-1950s, cars were generally equipped with 3-speed transmissions as standard equipment. 4-speed units began to appear on volume production models in the 1930s and 1950s and gained popularity in the 1960s. Some exotics had 5 speeds. In the 1970s, as fuel prices rose and fuel economy became an important selling feature, 4-speed transmissions with an overdrive 4th gear or 5 speeds were offered in mass-market automobiles and even compact pickup trucks, pioneered by Toyota. 6-speed transmissions started to emerge in high-performance vehicles in the early 1990s. 7-speed transmissions appeared on extreme high-end supercars, such as the 2005 Bugatti Veyron. In 2012, the Porsche 911 featured a 7-speed manual transmission, becoming the first of his class to support this feature, paving the way for the 2014 Chevrolet Corvette Stingray. Today, mass-market automotive manual transmissions are nearly all at least 5-speed. 4-speed manual transmission had fallen into almost total disuse by the end of the 1980s, having gradually become less common on cars during the 1980s. By the early 1990s, it was normally only found on cars with engines of around 1.0 liters. Recently Porsche announced the next generation 911 will be available with a 7-speed manual transmission, the first of its kind for a normal automobile, with the first 6 gear ratios the same as the 6-speed gearbox and the 7th gear being of a higher ratio. In 2013, the new 2014 Chevrolet Corvette Stingray will also feature a 7-speed manual transmission. It has been widely anticipated that for electric vehicles, clutches and multi-speed gearboxes would not be required, as electric motors can drive the vehicle both forward and reverse from 0 speed and typically operate over a wider speed range than combustion engines. Elimination of the gearbox represents a significant reduction in powertrain weight and complexity, and also removes a notable source of parasitic losses. The majority of first-generation consumer EVs have therefore been single-speed. However, current trends indicate that multi-speed gearboxes are likely to return for many future EVs. This allows the use of smaller, lower torque motors running at higher speeds to achieve both greater torque at the wheels for low-speed tractive effort, and higher top road speed. Modest efficiency gains are also possible by reducing the proportion of the time that the motors operate at very low speeds where efficiency is reduced. The wider speed range of motors means that the number of ratios required is lower than for combustion engine vehicles, with 2 to 4 speed designs emerging as the optimum depending on application. Initially the Tesla Roadster was intended to have a purpose-built 2-speed manual transmission, but this gearbox proved to be problematic and was later replaced with a fixed-ratio transmission. Gear ratios: the slowest gears in most automotive applications allow for 3 to 4 engine rotations for each output revolution. High, or top, gear in many earlier 3 or 4-speed manual transmissions locks the output shaft to spin at the same speed as the engine. 5 and 6-speed gearboxes are almost always overdrive in top gear, with the engine turning less than a full turn for each revolution of the output shaft, 0.81 for example. External overdrive. In the 1950s, 1960s, and 1970s, fuel-efficient highway cruising with low engine speed was in some cases enabled on cars equipped with 3 or 4-speed transmissions by means of a separate overdrive unit in or behind the rear housing of the transmission. This was actuated either manually while in high gear by throwing a switch or pressing a button on the gearstick knob or on the steering column, or automatically by momentarily lifting the foot from the accelerator with the car traveling above a certain road speed. Automatic overdrives were disengaged by flooring the accelerator, and a lockout control was provided to enable the driver to disable overdrive and operate the transmission as a normal transmission. Shaft and gear configuration: on a conventional rear-drive transmission, there are 3 basic shafts: the input, the output, and the counter shaft. The input and output together are called the main shaft, since they are joined inside the transmission so they appear to be a single shaft, although they rotate totally independently of each other. The input length of this shaft is much shorter than the output shaft. Parallel to the main shaft is the counter shaft. There are a number of gears fixed along the counter shaft, and matching gears along the output shaft, although these are not fixed, and rotate independently of the output shaft. There are sliding dog collars, or dog clutches, between the gears on the output shaft, and to engage a gear to the shaft, the collar slides into the space between the shaft and the inside space of the gear, thus rotating the shaft as well. One collar is usually mounted between 2 gears, and slides both ways to engage one or the other gears, so on a 4-speed there would be 2 collars. A front-drive transmission is basically the same, but may be simplified. There often are 2 shafts, the input and the output, but depending on the direction of rotation of the engine, 3 may be required. Rather than the input shaft driving the counter shaft with a pinion gear, the input shaft takes over the counter shaft's job, and the output shaft runs parallel to it. The gears are positioned and engaged just as they are on the counter shaft and output shaft of a rear drive. This merely eliminates one major component, the pinion gear. Part of the reason that the input and output are in line on a rear drive unit is to relieve torsional stress on the transmission and mountings, but this isn't an issue in a front drive as the gearbox is integrated into the transaxle. The basic process is not universal. The fixed and free gears can be mounted on either the input or output shaft, or both. The distribution of the shifters is also a matter of design. It need not be the case that all of the free rotating gears with selectors are on one shaft, and the permanently splined gears on the other. For instance, a 5-speed transmission might have the first to second selectors on the counter shaft, but the third to fourth selector and the fifth selector on the main shaft, which is the configuration in the 1998 Honda Civic. This means that when the car is stopped and idling in neutral with the clutch engaged and the input shaft spinning, the third, fourth and fifth gear pairs do not rotate. In some transmission designs there are actually 2 counter shafts, both driving an output pinion meshing with the front-wheel drive transaxle's ring gear. This allows the transmission designer to make the transmission narrower, since each counter shaft need only be half as long as a traditional counter shaft with 4 gears and 2 shifters. Freewheeling. Some automotive manual transmissions had freewheeling capability in the 1930s through 1960s. Clutch. In all vehicles using a transmission, a coupling device is used to separate the engine and transmission when necessary. This is because an internal combustion engine must continue to run when in use, although a few modern cars shut off the engine at a stoplight. The clutch accomplishes this in manual transmissions. Without it, the engine and tires would at all times be inextricably linked, and any time the vehicle stopped, the engine would stall. Without the clutch, changing gears would be very difficult, even with the vehicle moving already. Deselecting a gear while the transmission is under load requires considerable force. As well, selecting a gear requires the revolution speed of the engine to be held at a very precise value which depends on the vehicle speed and desired gear. The speeds inside the transmission have to match. In a car, the clutch is usually operated by a pedal. On a motorcycle, a lever on the left handlebar serves the purpose. When the clutch pedal is fully depressed, the clutch is fully disengaged, and no torque is transferred from the engine to the transmission. In this uncoupled state it is possible to select gears or to stop the car without stopping the engine. When the clutch pedal is fully released, the clutch is fully engaged and all of the engine's torque is transferred. In this coupled state, the clutch does not slip, but rather acts as rigid coupling to transmit power to the gearbox. Between these extremes of engagement and disengagement the clutch slips to varying degrees. When slipping it still transmits torque despite the difference in speeds between the engine crankshaft and the transmission input. Because this torque is transmitted by means of friction rather than direct mechanical contact, considerable power is wasted as heat. Properly applied, slip allows the vehicle to be started from a standstill, and when it is already moving, allows the engine rotation to gradually adjust to a newly selected gear ratio. Learning to use the clutch efficiently requires the development of muscle memory and a level of coordination. A rider of a highly tuned motocross or off-road motorcycle may hit, or fan the clutch when exiting corners to assist the engine in revving to the point where it delivers the most power. The clutch is typically disengaged by a thrust bearing that makes contact with pressure pedals on the clutch ring plate and pushes them inward to release the clutch pad friction. Normally the bearing remains retracted away from the pedals and does not spin. However, the bearing can be burned out, and damaged by using the clutch pedal as a footrest, which causes the bearing to spin continuously from touching the clutch plates. Gearshift Types, floor-mounted shifter. In most vehicles with manual transmission, gears are selected by manipulating a lever called a gear stick, shift stick, gear shift, gear lever, gear selector, or shifter connected to the transmission via linkage or cables and mounted on the floor, dashboard, or steering column. Moving the lever forward, backward, left, and right into specific positions selects particular gears. A sample layout of a 4-speed transmission is shown below. N marks neutral, the position wherein no gears are engaged and the engine is decoupled from the vehicle's drive wheels. The entire horizontal line is in neutral position, though the shifter is usually spring-loaded so it will return to the center of the N position if not moved to another gear. The A marks reverse, the gear position used for moving the vehicle backward. This layout is called the shift pattern. Because of the shift quadrants, the basic arrangement is often called an H pattern. The shift pattern is usually molded or printed on or near the gear knob. Typically, first gear is engaged to the top left position with second below, third up to the right with fourth, below, and so on. The only other pattern used in production vehicle manual transmissions is known as a dogleg gearbox pattern. This pattern locates first at bottom left position, second up and to the right with third below, fourth up and to the right, and so on. This pattern is found primarily in race and race-inspired vehicles. Placing the selection position for second gear above the position for third gear is desirable in racing as more frequent shifting occurs from second to third than from first to second. Independent of the shift pattern, the location of the reverse gear may vary. Depending on the particular transmission design, reverse may be located at the upper left extent of the shift pattern, at the lower left, at the lower right, or at the upper right. there is often a mechanism that allows selection of reverse only from the neutral position, or a reverse lockout that must be released by depressing the spring-loaded gear knob or lifting a spring-loaded collar on the shift stick, to reduce the likelihood of the driver inadvertently selecting reverse. 4 on the floor, 4-speed transmissions with floor-mounted shifters was sometimes referred to as 4 on the floor during the period when the steering column was the more common shifter location. The latter, often being the standard non-performance transmission, usually had only 3 forward speeds and was referred to as 3 on the tree. Most FR, front-engined, rear-wheel drive, cars have a transmission that sits between the driver and the front passenger seat. Floor-mounted shifters are often connected directly to the transmission. FF, front-engined, front-wheel drive, and RR, rear-engined, rear-wheel drive, cars often require a mechanical linkage to connect the shifter to the transmission. Column-mounted shifter. Some cars have a gear lever mounted on the steering column of the car. A 3-speed column shifter, which came to be popularly known as a 3 on the tree, began appearing in America in the late 1930s and became common during the 1940s and 1950s. If a U.S. vehicle was equipped with overdrive, it was very likely to be a Borg-Warner type, operated by briefly backing off the gas when above 28 mph to enable, and momentarily flooring the gas pedal to return to normal gear. The control simply disables overdrive for such situations as parking on a hill or preventing unwanted shifting into overdrive. Later, European and Japanese models began to have 4-speed column shifters with this shift pattern. A majority of North American spec vehicles for USA and Canada had a 3-speed column-mounted shifter. The first-generation Chevrolet GMC vans of 1964-70 vintage had an ultra-rare 4-speed column shifter. The column-mounted manual shifter disappeared in North America by the mid-1980s, last appearing in the 1987 Chevrolet pickup truck. Outside North America, the column-mounted shifter remained in production. All Toyota Crown and Nissan Cedric taxis in Hong Kong had the 4-speed column shifter until 1999 when automatic transmissions were first offered. Since the late 1980s or early 1990s, a 5-speed column shifter has been offered in some vans sold in Asia and Europe, such as Toyota Hiace, Mitsubishi L400 and the first-gen Fiat Ducato. Column shifters are mechanically similar to floor shifters, although shifting occurs in a vertical plane instead of a horizontal one. Because the shifter is further away from the transmission, and the movements at the shifter and at the transmission are in different planes, column shifters require more complicated linkage than floor shifters. Advantages of a column shifter are the ability to switch between the two most commonly used gears, a Euro second and third a Euro, without letting go of the steering wheel, and the lack of interference with passenger seating space in vehicles equipped with a bench seat. Console-mounted shifter. Newer small cars and MPVs, like the Suzuki Mr. Wagon, the Fiat Multipla, the Toyota Matrix, the Pontiac Vibe, the Chrysler AT platform cars, the Honda Element, the Honda Civic, and the Honda Avantia may feature a manual or automatic transmission gear shifter located on the vehicle's instrument panel, similar to the mid-1950s Chryslers and Powerglide Cavas. Console-mounted shifters are similar to floor-mounted gear shifters in that most of the ones used in modern cars operate on a horizontal plane and can be mounted to the vehicle's transmission in much the same way a floor-mounted shifter can. However, because of the location of the gear shifter in comparison to the locations of the column shifter and the floor shifter, as well as the positioning of the shifter to the rest of the controls on the panel, often require that the gear shift be mounted in a space that does not feature a lot of controls integral to the vehicle's operation or frequently used controls, such as those for the car stereo or car air conditioning, to help prevent accidental activation or driver confusion, especially in right-hand drive cars. More and more small cars and vans from manufacturers such as Suzuki, Honda, and Volkswagen are featuring console shifters in that they free up space on the floor for other car features such as storage compartments without requiring that the gear shift be mounted on the steering column. Also, the basic location of the gear shift in comparison to the column shifter makes console shifters easier to operate than column shifters. Sequential manual. Some transmissions do not allow the driver to arbitrarily select any gear. Instead, the driver may only ever select the next lowest or next highest gear ratio. Sequential transmissions often incorporate a synchro-less dog clutch engagement mechanism, in which case the clutch is only necessary when selecting first or reverse gear from neutral, and most gear changes can be performed without the clutch. However, sequential shifting and synchro-less engagement are not inherently linked, though they often occur together due to the environment in which these transmissions are used, such as racing cars and motorcycles. Sequential transmissions are generally controlled by a forward-backward lever, foot pedal, or set of paddles mounted behind the steering wheel. In some cases, these are connected mechanically to the transmission. In many modern examples, these controls are attached to sensors which instruct a transmission computer to perform a shift. Many of these systems can be switched into an automatic mode, where the computer controls the timing of shifts, much like an automatic transmission. Motorcycles typically employ sequential transmissions, although the shift pattern is modified slightly for safety reasons. In a motorcycle, the gears are usually shifted with the left foot pedal, the layout being this: 6-5-4-3-2 the pedal goes one step both up and down from the center, before it reaches its limit and is to be allowed to move back to the center position. Thus, changing multiple gears in one direction is accomplished by repeatedly pumping the pedal either up or down. Although neutral is listed as being between first and second gears for this type of transmission, it feels more like first and second gear are just further away from each other than any other two sequential gears. Because this can lead to difficulty in finding neutral for inexperienced riders, most motorcycles have a neutral indicator light on the instrument panel to help find neutral. The reason neutral does not actually have its own spot in the sequence is to make it quicker to shift from first to second when moving. Neutral can be accidentally shifted into, though most high-end, newer model motorcycles have means of avoiding this. The reason for having neutral between the first and second gears instead of at the bottom is that when stopped, the rider can just click down repeatedly and know that they will end up in first and not neutral. This allows a rider to quickly move his bike from a standstill in an emergency situation. This may also help on a steep hill on which high torque is required. It could be disadvantageous or even dangerous to attempt to be in first without realizing it, then try for a lower gear, only to get neutral. On motorcycles used on racetracks, the shifting pattern is often reversed, that is, the rider clicks down to upshift. This usage pattern increases the ground clearance by placing the rider's foot above the shift lever when the rider is most likely to need it, namely when leaning over and exiting a tight turn. The shift pattern for most underbone motorcycles with an automatic centrifugal clutch is also modified for two key reasons: to enable the less experienced riders to shift the gears without problems of finding neutral, and also due to the greater force needed to lift the gear shift lever. The gear shift lever of an underbone motorcycle has two ends. The rider clicks down the front end with the left toe all the way to the top gear and clicks down the rear end with the heel all the way down to neutral. Some underbone models such as the Honda Wave have a rotary shift pattern, which means that the rider can shift directly to neutral from the top gear, but for safety reasons this is only possible when the motorcycle is stationary. Some models also have gear position indicators for all gear positions at the instrument panel. Semi-manual: some new transmissions, for example, are conventional manual transmissions with a computerized control mechanism. These transmissions feature independently selectable gears but do not have a clutch pedal. Instead, the transmission computer controls a servo which disengages the clutch when necessary. These transmissions vary from sequential transmissions in that they still allow non-sequential shifts. The SMG system formerly used by BMW, for example, could shift from 6th gear directly to 4th gear. An early version of this type of transmission was the Autostick, which was used in the Volkswagen Beetle and Carmen Guy from 1967 to 1976, where the clutch was disengaged by servo when the driver pushed downward slightly on the gear shift lever. This was a 3-speed unit. In the case of the early second-generation Saab 900, a sensonic option was available where gears were shifted with a conventional shifter, but the clutch is controlled by a computer. See semi-automatic transmission for more examples. Short shifter. A short shifter, also known as a short-throw shifter, is the result of an automotive aftermarket modification of the manual transmission's stick shift, either by modification of the existing stick shift or, alternately, by the replacement of the entire part. The purpose of the modification is to mechanically reduce time between the changing of gears while accelerating or decelerating, thus improving the automobile's performance. The modification of the existing stick shift, also known as a manual gear stick, can take two forms, either the physical shortening of the existing stick shift, known in the industry as chopping, or bending. By reducing the length of the stick shift, the distance it must travel to change gears is effectively reduced, thus reducing the time spent shifting. At the same time, the amount of force required to shift increases due to a shorter lever. Some major car manufacturers such as Subaru, Mazda and Porsche offer short shifters as stock modifications, such as in the Subaru Impreza WRX, Subaru Impreza WRX STI, Mazda Miata, and as an option such as in the Porsche 911. Finger shift. In Japan, finger shift is used at bus 1. Its system is made in Robert Bosch GmbH. Benefits: fuel economy. The manual transmission couples the engine to the transmission with a rigid clutch instead of the torque converter on an automatic transmission or the V-belt of a continuously variable transmission, which slip by nature. Manual transmissions also lack the parasitic power consumption of the automatic transmission's hydraulic pump. Because of this, manual transmissions generally offer better fuel economy than automatic or continuously variable transmissions. However, the disparity has been somewhat offset with the introduction of locking torque converters on automatic transmissions. Increased fuel economy with a properly operated manual transmission vehicle versus an equivalent automatic transmission vehicle can range from 5% to about 15% depending on driving conditions and style of driving. The lack of control over downshifting under load in an automatic transmission, coupled with a typical vehicle engine's greater efficiency under higher load, can enable additional fuel gains from a manual transmission by allowing the operator to keep the engine performing under a more efficient load RPM combination. This is especially true for older models, as advances like variable valve timing allow better performance over a broader RPM range. In recognition of this, many current models come with manual modes, or overrides on automatic models, although the degree of control varies greatly by the manufacturer. Also, manual transmissions do not require active cooling, and because they are, mechanically, much simpler than automatic transmissions, they generally weigh less than comparable automatics, which can improve economy and stop-and-go traffic. However, this gap in economy is being rapidly closed, and many mid to higher-end model automatic cars now get better economy than their standard spec counterparts. This is in part due to the increasing impact of computers coordinating multiple systems, particularly in hybrid models in which the engine and drive motors must be managed. Longevity and cost. Durability. Because manual transmissions are mechanically simpler, are more easily manufactured, and have fewer moving parts than automatic transmissions, they require less maintenance and are easier as well as cheaper to repair. Due to their mechanical simplicity, they often last longer than automatic transmissions when used by a skilled driver. Typically, there are no electrical components, pumps and cooling mechanisms, other than an internal switch to activate reversing lighting. These attributes become extremely vital with a vehicle stuck in mud, snow, etc. The back-and-forth rocking motion of the vehicle drivers used to dislodge a stuck vehicle can prove fatal to automatic transmissions. The vast majority of automatic transmission hydraulics are not designed to be shifted between drive and reverse multiple times in rapid sequence. Clutches are a wear item which may need to be replaced at some point in the vehicle's lifespan, however the service life of the clutch depends on the skill of the driver and the operating conditions that it is subjected to. Cost. The price of a new car with a manual transmission will commonly be lower than the same car with an automatic transmission. Most new cars are available in manual or automatic transmission versions. There is almost always a difference in cost between the two. Typically, manual transmission vehicles cost less than automatic transmissions. While the price difference is not drastic, typically only around $1,000, they are less expensive. The owner of the car can use the $1,000 they saved by buying a manual transmission vehicle for other things, such as a stereo, a navigation system, or other upgrades. The Chevy Cruze 2LT with a manual transmission's base price is $22,120, while the base price of the automatic is $23,405. That is a difference of $1,285. This means that the purchaser of a manual transmission would pay that much less for the same exact car, simply because it has a manual transmission. This money could be put into adding features, such as a sunroof, different wheels and tires, or the optional navigation system Chevy offers. The owner of a manual transmission would have more features for the same price as the basic automatic transmission vehicle. Lubrication. Most manual transmissions rely on splash lubrication, although some 5-speed Rover gearboxes did incorporate an oil pump. The problem with splash lubrication is that it is speed dependent. There are centrifugal effects, hydrodynamic effects and effects from the gears working as pumps. If a gearbox is fitted with perspex windows and run on a test rig, these effects can be observed. As the gearbox is run through its rev range, the oil jets will switch over and move around. Research on the Austin Mark C 1500 gearbox showed that one of the ball races was running dry at 80 miles per hour. The solution was to alter the casting to include a small projection that would intercept the main oil jet that was present at 80 miles per hour and disperse it. This small modification enabled the later Mark C 1750 gearbox to be relatively trouble-free. 4-speed gearboxes seldom show these problems because at top speed they are basically a solid shaft and the gears are not transmitting power. Performance and control. Manual transmissions have generally offered a wider selection of gear ratios. Many vehicles offer a 5-speed or 6-speed manual, whereas the automatic option would typically be a 4-speed. This is generally due to the increased space available inside a manual transmission compared with an automatic, since the latter requires extra components for self-shifting, such as torque converters and pumps. However, automatic transmissions are now adding more speeds as the technology matures. ZF currently manufactures 7 and 8-speed automatic transmissions. ZF is also planning a 9-speed automatic for use in front-wheel drive vehicles. The increased number of gears allows for better use of the engine's power band, resulting in increased fuel economy by staying in the most fuel-efficient part of the power band, or higher performance, thereby remaining closer to the engine's peak power rating. Even with more forward speeds and the potential of designing more forward gears to offer higher speed and/or torque, the manual transmission remains smaller and much more compact than its larger, automatic cousin, as referenced by the 991 generation of the Porsche 911 and the 2014 Chevy Corvette, which has a 7-speed manual transmission. Engine braking. In contrast to most manual gearboxes, most automatic transmissions have far less effective engine braking. This means that the engine does not slow the car as effectively when the automatic transmission driver releases the engine speed control. This leads to more usage of the brakes in cars with automatic transmissions, bringing shorter brake life. Brakes are also more likely to overheat in hilly or mountainous areas, causing reduced braking ability, brake fade and the potential for complete failure with the automatic transmission vehicle. Drawbacks, complexity and learning curve. For most people, there is a slight learning curve with a manual transmission, which may be intimidating and unappealing for an inexperienced driver. Because the driver must develop a feel for properly engaging the clutch, an inexperienced driver will often stall the engine. Most drivers can learn how to drive a car with a manual transmission in as little as an hour, although it may take weeks before it becomes second nature. Additionally, if an inexperienced driver selects an inappropriate gear by mistake, damage to mechanical components and even loss of control may occur. Shifting speed. Automatic transmissions can shift ratios faster than a manual gear change can be accomplished, due to the time required for the average driver to push the clutch pedal to the floor and move the gear stick from one position to another. This is especially true in regards to dual-clutch transmissions, which are specialized computer-controlled automatic transmissions that operate more like a manual transmission than a traditional automatic one. Ease of use, because manual transmissions require the operation of an extra pedal, and keeping the car in the correct gear at all times, they require a bit more concentration, especially in heavy traffic situations. The automatic transmissions, on the other hand, simply require the driver to speed up or slow down as needed, with the car doing the work of choosing an appropriate gear. Manual transmissions also place a greater workload on the driver in heavy traffic situations, when the driver must operate the clutch pedal quite often. Because the clutch pedal can require a substantial amount of force, especially on large trucks, and the long pedal travel compared to the brake or accelerator requires moving the entire leg, not just the foot near the ankle, a manual transmission can cause fatigue, and is more difficult for weak or injured people to drive. Additionally, because automatic transmissions can be driven with only one foot, people with one leg that is missing or impaired can still drive, unlike the manual transmission that requires the use of 2 feet at once. Likewise, manual transmissions require the driver to remove one hand periodically from the steering wheel while the vehicle is in motion, which can be difficult or impossible to do safely for people with a missing or impaired arm, and requires increased coordination, even for those with full use of both hands. Stopping on hills, the clutch experiences most of his wear in first gear because moving the car from a standstill involves a great deal of friction at the clutch. When accelerating from a standstill on an incline, this problem is made worse because the amount of work needed to overcome the acceleration of gravity causes the clutch to heat up considerably more. For this reason, stop-and-go driving and hills tend to have an effect on the clutches to a certain degree. Automatic transmissions are better suited for these applications because they have a hydraulic torque converter which is externally cooled, unlike a clutch. Torque converters also do not have a friction material that rubs off over time like a clutch. Some automatics even lock the output shaft so that the car cannot roll backwards when beginning to accelerate up an incline. To reduce wear in these applications, some manual transmissions will have a very low, granny gear which provides the leverage to move the vehicle easily at very low speeds. This reduces wear at the clutch because the transmission requires less input torque. However, the issue of handling stops on hills is easy to learn. Many drivers use the parking brake to prevent the car from rolling backward when starting to accelerate up a steep hill. This saves precious clutch life. Some modern cars such as the Dodge Challenger and most Subaru models have a hill start assist feature. The vehicle's computer applies just enough brake pressure to prevent the car from rolling backwards. This allows the driver to start normally with no additional effort, even on steep hills. Starting on a hill with the aid of the parking brake is not always possible since in recent cars that feature an electric park brake the parking brake can only be released when the brake pedal is engaged. Applications and popularity. Sports cars are also often equipped with manual transmissions because they offer more direct driver involvement and better performance, though this is changing as many automakers move to faster dual-clutch transmissions, which are generally shifted with pedals located behind the steering wheel. For example, the 991 Porsche 911 GT3 uses Porsche's PDK. Off-road vehicles and trucks often feature manual transmissions because they allow direct gear selection and are often more rugged than their automatic counterparts. Conversely, manual transmissions are no longer popular in many classes of cars sold in North America, Australia and some parts of Asia, although they remain dominant in Europe, Asia, Africa and Latin America. Nearly all cars are available with an automatic transmission option, and family cars and large trucks sold in the US are predominantly fitted with automatics. However, in some cases if a buyer wishes she can have the car fitted with a manual transmission at the factory. In Europe most cars are sold with manual transmissions. Most luxury cars are only available with an automatic transmission. In most cases where both transmissions are available for a given car, automatics are an at-cost option, but in some cases the reverse is true. Some cars, such as rental cars and taxis, are nearly universally equipped with automatic transmissions in countries such as the US, but the opposite is true in Europe. As of 2008, 75.2% of vehicles made in Western Europe were equipped with manual transmission, versus 16.1% with automatic and 8.7% with other. when a driver takes the licensing road test using an automatic transmission in some places, the resulting license is restricted to the use of automatic transmissions. This is the case in countries such as New Zealand, the European Union with the exception of member countries that opt to disallow road tests on automatic vehicles completely, China, Dominican Republic, Israel, Jordan, Norway, Philippines, Singapore, South Africa, South Korea, Sri Lanka, Switzerland, and the UAE. This treatment of the manual transmission skill seems to maintain the widespread use of the manual transmission. As many new drivers worry that their restricted license will become an obstacle for them where most cars have manual transmissions, they make the effort to learn with manual transmissions and obtain full licenses. Some other countries go even further, whereby the license is granted only when a test is passed on a manual transmission. In Denmark and Brazil, drivers are allowed to take the test on an automatic if they are handicapped, but with such a license they will not be allowed to drive a car with a manual transmission. Truck transmissions. Some trucks have transmissions that look and behave like ordinary car transmissions. These transmissions are used on lighter trucks, typically have up to 6 gears, and usually have Synchromesh. For trucks needing more gears, the standard H pattern can get very complicated, so additional controls are used to select additional gears. The H pattern is retained, then an additional control selects among alternatives. In older trucks, the control is often a separate lever mounted on the floor or more recently a pneumatic switch mounted on the H lever. In newer trucks the control is often an electrical switch mounted on the H lever. Multi-control transmissions are built in much higher power ratings, but rarely use Synchromesh. There are several common alternatives for this shifting pattern. Usual types are, range transmissions use an H pattern through a narrow range of gears, then a range control shifts the H pattern between high and low ranges. For example, an 8-speed range transmission has an H-shift pattern with 4 gears. The first through 4th gears are accessed when low range is selected. To access the 5th through 8th gears, the range selector is moved to high range, and the gear lever again shifted through the 1st through 4th gear positions. In high range, the 1st gear position becomes 5th, the 2nd gear position becomes 6th, and so on. Splitter transmissions use an H pattern with a wide range of gears, and the other selector splits each sequential gear position in 2, 1st gear is in 1st position low split, 2nd gear is in 1st position high split, 3rd gear is in 2nd position low split, 4th gear is in 2nd position high split, and so on. Range splitter transmissions combine range splitting and gear splitting. This allows even more gear ratios. Both a range selector and a splitter selector are provided. Although there are many gear positions, shifting through gears usually follows a regular pattern. For example, a series of upshifts might use move to splitter direct, move to splitter overdrive, move shift lever to no A2 and move splitter to underdrive, move splitter to direct, move splitter to overdrive, move shift lever to no A3 and move splitter to underdrive, and so on. In older trucks using floor-mounted levers, a bigger problem is common gear shifts require the drivers to move their hands between shift levers in a single shift, and without Synchromesh, shifts must be carefully timed or the transmission will not engage. For this reason, some splitter transmissions have an additional under range, so when the splitter is already in under it can be quickly downshifted again, without the delay of a double shift. Today's truck transmissions are most commonly range splitter. The most common 13-speed has a standard H pattern, and the pattern from left upper corner is as follows: R, down to L, over and up to 1, down to 2, up and over to 3, down to 4. The butterfly range lever in the center front of the knob is flipped up to high range while in 4th, then shifted back to 1. The 1 through 4 positions of the knob are repeated. Also, each can be split using the thumb-actuated under overdrive lever on the left side of the knob while in high range. The thumb lever is not available in low range, except in 18 speeds. 1 through 4 in low range can be split using the thumb lever and L can be split with the butterfly lever. L cannot be split using the thumb lever in either the 13 or 18 speed. The 9-speed transmission is basically a 13-speed without the under-overdrive thumb lever. Truck transmissions use many physical layouts. For example, the output of an N-speed transmission may drive an M-speed secondary transmission, giving a total of N-M gear combinations. For example, a 4-speed main box and 3-speed splitter gives 12 ratios. Transmissions may be in separate cases with a shaft in between. In separate cases bolted together. Or all in one case, using the same lubricating oil. The second transmission is often called a brownie, or brownie box after a popular brand. With a third transmission, gears are multiplied yet again, giving greater range or closer spacing. Some trucks thus have dozens of gear positions, although most are duplicates. Sometimes a secondary transmission is integrated with the differential in the rear axle, called a 2-speed rear end. 2-speed differentials are always splitters. In newer transmissions, there may be 2 countershafts, so each main shaft gear can be driven from one or the other countershaft. This allows construction with short and robust countershafts, while still allowing many gear combinations inside a single gear case. Heavy-duty transmissions are almost always non-synchromesh. One argument is synchromesh adds weight that could be payload, is one more thing to fail, and drivers spend thousands of hours driving so can take the time to learn to drive efficiently with a non-synchromesh transmission. Heavy-duty trucks driven frequently in city traffic, such as cement mixers, need to be shifted very often and in stop-and-go traffic. Since few heavy-duty transmissions have synchromesh, automatic transmissions are commonly used instead, despite their increased weight, cost, and loss of efficiency. Heavy trucks are usually powered with diesel engines. Diesel truck engines from the 1970s and earlier tend to have a narrow power band, so need many close-spaced gears. Starting with the 1968 Maxidine, diesel truck engines have increasingly used turbochargers and electronic controls that widen the power band, allowing fewer and fewer gear ratios. A transmission with fewer ratios is lighter and may be more efficient due to fewer transmissions in series. Fewer shifts also makes the truck more drivable. As of 2005, fleet operators often use 9, 10, 13 or 18-speed transmissions, but automated manual and semi-automatic transmissions are becoming more common on heavy vehicles, as they can improve efficiency and drivability, reduce the barrier to entry for new drivers, and may improve safety by allowing the driver to concentrate on road conditions. Crash gearbox. A crash gearbox, also known as a crash box, is a transmission type used in old cars, trucks, and other automotive vehicles. It is more properly called a sliding mesh gearbox and has the nickname crash, because it is difficult to change gears, so gear changes are often accompanied by loud noises. The etymology of crash is probably clash. In a sliding mesh gearbox, individual gears are mounted so they always engage the shaft, but gears on one shaft can be moved axially. To engage a particular pair of gears, one gear is slid axially until it fully engages a gear on the other shaft. If the gear shafts are spinning so the two gears have the same surface velocity, the gears are relatively easy to engage. However, if velocities are mismatched, the gears tend to bounce off each other at first contact and resist engagement. Thus, gear engagement relies on the driver carefully matching speeds, typically through practice and intuition. In contrast, newer constant mesh transmissions use gears that are held axially, but gears on one shaft spin freely on the shaft. Gear pairs in the transmission are always in mesh, though at most one is engaged at any time. Each free-spinning gear has a dog clutch which is engaged by an axial sliding collar that transfers power to the shaft. The dog clutch may be plain, also called non-synchromesh, or may use an additional synchromesh mechanism that helps get the parts moving at the same speed to assist engagement. Many constant mesh transmissions use a sliding mesh gear for reverse, but since reverse is only engaged from near a stop, it is still easy to engage. A constant mesh transmission offers several advantages over a sliding mesh design. First, the dog clutch is designed for the task, rather than asking the gear to do dual duty of power transmission and sliding engagement. Second, the dog clutch is typically smaller in diameter than the gear it controls, so absolute speeds of the engaging parts are lower, aiding engagement. Thus, while a non-Synchromesh transmission still relies on the operator to match speeds, gears are easier to engage. Third, a constant mesh transmission can easily use helical gears which are smoother, quieter, and can carry more torque for a given size of gear. Fourth, a constant mesh transmission can use Synchromesh for easier shifting. While many heavy vehicle transmissions do not use it, most medium and light-duty automotive transmissions do. Maintenance: because clutches use changes in friction to modulate the transfer of torque between engine and transmission, they are subject to wear in everyday use. A very good clutch, when used by an expert driver, can last hundreds of thousands of kilometers. Weak clutches, abrupt downshifting, inexperienced drivers, and aggressive driving can lead to more frequent repair or replacement. Manual transmissions are lubricated with gear oil or engine oil in some cars, which must be changed periodically in some cars, although not as frequently as the automatic transmission fluid in a vehicle so equipped. Gear oil has a characteristic aroma due to the addition of sulfur-bearing anti-wear compounds. These compounds are used to reduce the high sliding friction by the helical gear cut of the teeth. On motorcycles with wet clutches, there is usually nothing separating the lower part of the engine from the transmission, so the same oil lubricates both the engine and transmission. The original Mini placed the gearbox in the oil sump below the engine, thus using the same oil for both. The clutch was however a fairly conventional dry plate clutch. See also, automatic transmission, diesel-electric transmission, freewheel, gear ratio, hydraulic transmission, non-synchronous transmission, overdrive, pre-selector gearbox, top-loader transmission, Borg-Warner T56, G56 manual transmission, New Venture Gear 5600 transmission, New Venture Gear 4500 transmission, New Venture Gear 3500 transmission. References